In this video, we'll start talking about groups. First, I'll introduce binary operations on a set. Then we'll give the definition of a group and we'll look at some examples. A binary operation on a set G is just a rule that tells us how to combine two elements of G to produce a new element. You can think about this as a rule like addition or multiplication that we're using to try to impose some kind of algebraic structure on the set G. Now, to be a little more mathematical, a binary operation on G is really a function from the Cartesian product G cross G to itself. We'll denote this function by various symbols. Here I'm just using a star, and usually instead of writing star of AB for two elements A and B of G, we'll just write A star B instead. Now, here's a big list of rules that you can try to impose on different sets. And I want to warn you ahead of time that not all of these rules end up being binary operations on the sets. So what I'd like to do is filter out the rules that are binary operations from the ones that are not. As we go through this video, we'll continue to filter this set more and more until we can finally identify which ones of these sets together with the corresponding rules end up forming groups. Let's start with the more familiar objects on the left-hand side here. Remember that the requirement to be a binary operation is just that you have a rule which maps two elements of your set to another element of the same set. That's not too difficult to satisfy, and a lot of these are going to end up being binary operations, but a few of them are not. The ones that are not are division on Z, Q, R, or C, division on the non-zero integers, and the dot product on R3. See if you can think about the reasons why those ones that I pointed out end up not being binary operations, and I'll show you the answer on the next slide. Now, on the right-hand column, there are a couple of objects here that we haven't defined yet. When we write M sub mn of R, we mean the collection of m by n matrices with coefficients in R. And when we write GL2R, we mean the collection of 2 by 2 matrices with real coefficients and with determinant not equal to 0. Everything else here should be familiar to you, so maybe you can already see which ones of these operations satisfy our definition of a binary operation and which ones don't. Well, out of the list that I just showed you, here are the rules that define binary operations on the corresponding sets. Remember, as I said before, that to be a binary operation just means that these rules take two elements of the corresponding set and then produce another element of the same set. I don't really want to go through each of these examples individually because a lot of them are easy to see, but two that I will focus on are the two on the bottom right here, multiplication on GL2R and the symmetric difference on the power set of a set S. The reason why multiplication on GL2R is a binary operation has to do with the property of determinants of 2 by 2 matrices. If I choose two matrices in this set and I multiply them together, the determinant of the product of the matrices is the product of the determinants. Since any two matrices in this set must have non-zero determinant, their product must also be a 2 by 2 matrix with real coefficients and non-zero determinant. Therefore, multiplication is a binary operation on GL2R. It should also be pretty clear that the symmetric difference is a binary operation on the power set of an arbitrary set S. That's just because the symmetric difference of two subsets of S is just another subset of S. Now, of the rules that I showed you before, here are the four that turn out not to be binary operations on the corresponding sets. First of all, division is not a binary operation on Z, Q, R, or C. And there's a very simple reason why. It's because 1 divided by 0 is not even defined. So for example, division is not a function from Z cross Z to Z because it's not defined at certain points. Well, now you may wonder, what about if we throw 0 out of these sets? Well, that does fix the problem for the sets Q, R, and C, because division of any two non-zero rational, real, or complex numbers is defined, and again produces a rational, real, or complex number respectively. That's the reason why division on Q minus 0 or R minus 0 or C minus 0 was listed as one of our binary operations on the previous slide. However, throwing 0 out of the set of integers still doesn't make division on the resulting set a binary operation. And the reason is because when you combine certain pairs of integers using this binary operation, the result is no longer an element of the set. For a simple example, 1 divided by 2 is a well-defined rational number, but it's not an element of the set of non-zero integers. That means that division is not a binary operation on this set. Well, how about the dot product on R3? Writing elements of R3 as vectors in this example, if I take the dot product of two vectors in R3, I end up with a real number, not with another element of R3. So this is also not a binary operation. And finally, how about addition on the collection of 2 by 2 real matrices with non-zero determinant? Well, when we were working with multiplication on this set, we said that it was a binary operation, and there we relied on the multiplicativity of the determinant. But if we're considering addition on this set, then it's not going to be a binary operation. And the reason is that just because you have two matrices with non-zero determinant, that doesn't guarantee that the sum of the two matrices is also going to have non-zero determinant. A simple example, take A to be the identity matrix and take B to be the negative of the identity matrix. Both of these matrices have determinant 1, so they're both elements of GL2R. But when you add them together, you get the zero matrix, which has determinant 0. So the sum of these two matrices is no longer an element of GL2R. And that shows that addition on GL2R is not a binary operation. Next, let's talk about a couple of properties that a binary operation could or could not have. The two main properties that we're interested in looking at are associativity and commutativity. So if we have a binary operation star on a set G, we say that it's associative if for any three elements A, B, and C of G, when you compute A star B and then star that with C, you get the same thing as when you compute A star with B star C. If we say that the binary operation is commutative, then it means that for any two elements A and B and G, A star B is the same as B star A. Now let's go back and look at the binary operations that we've collected to see which ones are associative and which ones are commutative. Some of these are things that we already know, like for example, we already know that addition on any one of the sets listed here is an associative and commutative binary operation. What about subtraction on these sets? First, let's consider associativity. If you choose three elements of one of these sets, A, B, and C, and then you compute A minus B and then subtract C, what you get is the same as if you take A minus B plus C. But the thing I hope you realize is that that's not going to be equal to A minus B minus C in general. Notice that I added the words in general here because there are some choices of A, B, and C for which the left and right hand sides are equal. Because of that fact, I think it's generally simpler in a situation like this if you just give an example with numbers. So for example, if I take A, B, and C to all be 1, then computing A minus B minus C gives me -1. But computing A minus B minus C gives me 1. Since I got two different answers when I put the parentheses in the two different places, this binary operation is not associative. Okay, next let's think about commutativity. Well, I think we're all pretty familiar with the fact that subtraction is not in general a commutative operation. But again, I think it's a good idea just to list out an example. So for example, if you take A equals 1 and B equals 0, then A minus B is not the same as B minus A. And that means that this binary operation is not commutative. Okay, moving on to our next binary operation, multiplication on Z, Q, R, or C is again a very familiar binary operation, and I think we all realize that it's both associative and commutative. So I'm not going to try to explain anything more about that. How about the binary operation of division on the non-zero rationals or the non-zero reals or the non-zero complex numbers? Well, I think if you just play around with a few examples, you're going to realize pretty quickly that this is not an associative binary operation. So in the example that I've given here, I've just shown that 1 divided by 2 divided by 2 is not the same as 1 divided by 2 divided by 2. Similarly, it's pretty easy to see that this binary operation is not commutative. And here's an example which shows that. How about the cross product on R3? Well, here again, it's a good idea just to play around with some examples. And I think that if you do that, you're going to convince yourself pretty quickly that this binary operation is neither associative nor commutative. You've probably seen examples like this when you were introduced to the cross product. But for example, if you compute I cross I, you get the 0 vector. And if you then cross that with the j vector, you still get the 0 vector. But if you move the parentheses over and first compute I cross j, then in the second component here you get the k vector. And when you compute I cross k, you get the negative of the j vector, which is not the same as the 0 vector. That shows that the cross product is not associative. Here's an example to show that it's not commutative. If you compute I cross j, you get k. But if you compute j cross I, you get -k. Therefore, the cross product is also not commutative. How about addition on the collection of m by n matrices with real coefficients? Well, when you add two m by n matrices, you just add the corresponding coefficients. And since addition of real numbers is associative and commutative, it should be pretty clear that addition of m by n matrices with real coefficients is also associative and commutative. How about multiplication of n by n matrices with real coefficients? I think I forgot to mention this before, but it's important that the number of rows and columns here are both n, because that guarantees that the product of two matrices in this set is well defined, and that it's another element of the set. Okay, anyway, you may be familiar with the fact that multiplication of matrices is an associative operation. That's not something which is entirely trivial, but hopefully you've seen that before, maybe in linear algebra or something. Anyway, I'm not going to prove it, but multiplication of n by n matrices is an associative operation. If you're somewhat familiar with matrices, you probably also realize that matrix multiplication is not commutative, unless of course we happen to be in the degenerate case when n is 1, and then we're really just talking about multiplication of real numbers. As long as n is bigger than 1 though, multiplication on m, n, and r is not a commutative operation. That does need a little bit of justification, and it's worth giving a little argument to justify it here. So here you go. If you take A to be the n by n matrix with all 1s along the diagonal, a 2 in the top right position, and 0s everywhere else, and if you take B to be the matrix with a 2 in the top left position, 1s everywhere else along the diagonal, and 0s everywhere else, then it turns out that AB is not equal to BA. One way to very quickly verify that is to look at the 1n coefficient of the matrix on the left and compare it to the 1n coefficient of the matrix on the right. The 1n coefficient of the matrix on the left is what you get by dotting the first row of the matrix A with the nth column of the matrix B, so it's a 2. And the 1nth coefficient of the matrix BA is what you get by dotting the first row of B with the nth column of A, so it's a 4. Since those two coefficients are not equal, the two matrices themselves are not equal. And this shows that multiplication is not a commutative operation on m, n, and r when n is bigger than 1. Now for essentially the same reason, multiplication on GL2R is also an associative but not a commutative operation. Now let's consider our final binary operation, which was the symmetric difference operator on the power set of a set S. We already remarked in our video on set operations that this binary operation is a commutative operation, because if you compute A triangle B for any sets A and B in the power set of S, you'll get the same thing as if you compute B triangle A. Now it turns out that this is also an associative binary operation, and that's something which does require a proof, but I can at least give you a flavor for why it's true by showing you the following collection of Venn diagrams. The top left Venn diagram illustrates the set A triangle B, and when I take the symmetric difference of that with the set C, I get the set of everything that's in A triangle B, but not C, together with the set of everything that's in C, but not A triangle B. So I get a set that looks like this. On the other hand, if I start with B triangle C, and then I compute A triangle that, I end up with the same picture. And so however I decide to put the parentheses on my original sets, I end up with the same set. Now, like I said before in my video on set operations, Venn diagrams are not usually considered a rigorous form of mathematical proof. But at least this gives you some indication that the result is true, and that the symmetric difference on the power set of a set S is an associative operation. Okay, well, at long last, we've arrived at the definition of a group. A group is a pair consisting of a set G together with a binary operation star on G, satisfying three properties. First of all, the binary operation star must be associative. Secondly, there must exist an element E in G, with the property that, for any G in G, E star G and G star E are both equal to G. And finally, for any G in G, there must exist an element H in G with the property that both G star H and H star G are equal to E. The element E in the second property here is what's called an identity element. If your binary operation is something like addition, then the identity element plays the role of 0. And if your binary operation is something like multiplication, then the identity element plays the role of 1. But in general, this is the definition of the identity element. I said the identity element, and I should have said an identity element. But it doesn't really matter, because it's going to turn out later that in a group, the identity element is unique, so that there's only one. But anyway, an identity element is just an element which satisfies the property that when you combine it with any element of the group, either as E star G or as G star E, you don't change the element G. The second property here is also referred to as existence of identity. Now the third property here claims that for any element G in G, I can find an element H in G with the property that when I combine it using my binary operation with G, either as G star H or as H star G, I get back the identity. That element H is what we refer to as the inverse of G. If your binary operation is something like addition, then you can think about H as being something like minus G. And if your binary operation is something more like multiplication, then you can think about H as being something like G inverse. In any case, this third property is saying that every element of the group has an inverse, so we refer to it as existence of inverses. Now, you might notice that in this definition, we required the binary operation star to be associative, but we didn't say anything about commutativity. Well, commutativity is an extra property which may or may not be satisfied in a group. If we have a group where the binary operation is commutative, then we call it an abelian group. But there are many more interesting examples of groups where the binary operation is not commutative, and those are called non-abelian groups. We're going to see lots of examples of abelian and non-abelian groups in the coming videos. Now what I'd like to do next is go through all the binary operations that we've collected so far and decide whether or not the corresponding sets, together with those binary operations, form groups. Because of property number 1 here, we can ignore all of the binary operations which are not associative, so we'll focus just on the ones that were associative. First, let's look at the integers under the binary operation of addition. Since we already decided that addition on the integers is an associative binary operation, we just need to think about whether or not there's an identity element, and then whether or not every integer has an inverse with respect to this binary operation. First of all, for the identity element, we're looking for an integer with the property that, when we add it to any other integer, either on the left or on the right, we don't change the other integer. Of course, since the binary operation here is addition, for an identity element, we can just take the integer 0. Then for any integer n, 0 plus n and n plus 0 are both equal to n. So that shows the existence of an identity. For inverses, we want to know whether or not, for every integer n, there exists an integer m with the property that n plus m equals m plus n equals 0. Hopefully it's pretty clear that for any integer n, we can just take m to be minus n. Minus n is another integer, and of course it has the property that n plus m equals the identity element, which is 0 in this case. That shows existence of inverses, so we know that the integers together with addition are a group. Now, since the binary operation is commutative in this case, this is an example of an abelian group. Essentially, the same argument shows that the rational numbers under addition, the real numbers under addition, and the complex numbers under addition are all also abelian groups. These are some of the simplest examples. Now let's consider the integers under multiplication, which we also decided was an associative binary operation. Therefore, to decide whether or not this is a group, we just need to check whether or not there's an identity element, and then whether or not every element has an inverse with respect to multiplication. For the identity element, this time we're looking for an integer with the property that when we multiply it with any other integer, from the left or from the right, it doesn't change the other integer. Since the operation is multiplication, this time we can take the integer 1 as an identity element. Then it's clear that for any integer n, 1 times n equals n times 1 equals n. So there is an identity element in the integers with respect to multiplication. Now let's consider the question of whether or not every integer has an inverse with respect to multiplication. In other words, is it true that for every integer n, there exists an integer m with the property that mn equals nm equals 1? Well, of course that's not true, and one example of an integer that doesn't have a multiplicative inverse is the integer 2. If 2 times m were equal to 1, that would force m to be a half, but a half is not an integer. Therefore, 2 is an example of an integer which doesn't have an inverse with respect to multiplication. We can call it a non-invertible element in the integers with respect to multiplication. Since there are some elements which don't have inverses, the integers together with multiplication turns out to not be a group. Well, let's see if the story is any different when we consider the rationals or the reals or the complex numbers under multiplication. Here we can still take 1 to be an identity element, since 1 times any rational number or real number or complex number is just that number itself. And here we don't have exactly the same problem that we had when we were looking at the integers, because for example, if we take the rational number 2, the number 1/2 is a multiplicative inverse, and it's again a rational number. And in fact, the multiplicative inverse of any number in one of these sets will just be the reciprocal of the number, provided that the number itself is not 0. But the problem here is with the number 0, which is an element of all three of these sets. If there were a multiplicative inverse m of 0, it would have to be another number in one of these sets with the property that 0 times m is equal to 1. But since 0 times anything is equal to 0, the multiplicative inverse of 0 does not exist. And so, even though there's just one element here that failed to have an inverse, it means that these three sets, together with the binary operation of multiplication, are not groups. Well now, what if we try to fix the problem here by throwing out the number 0 and considering multiplication on the non-zero rationals or reals or complex numbers? Again, we can take the multiplicative identity to be 1, and for any element of these sets, there is a well-defined multiplicative inverse, which is just the reciprocal of the number. And so now we fix the problems that we saw in the previous two examples, and all three of these turn out to be abelian groups. Abelian, of course, because multiplication of rational or real or complex numbers is commutative. Next, let's consider the collection of m by n matrices with real coefficients together with the binary operation of addition. Now, I just want to keep reminding you that when you're trying to check whether or not something is a group, there are three things that you need to check. First of all, you need to check that the binary operation is associative, which we've done in this case. Second, you need to check for existence of an identity element. And third, you need to check for existence of inverses. Well, since the binary operation here is addition of matrices, for the identity element we can take the zero matrix, which is the matrix of all zeros. It's clear that if we add this to any other m by n matrix with real coefficients, either from the left or from the right, we're not going to change the other matrix. So this is an identity element. It's also pretty easy to see in this case that the additive inverse of a matrix in this set is just the negative of the matrix. In other words, it's the matrix where each of the components are the negatives of the corresponding components in A. Since addition of m by n matrices is defined component-wise, when you add a matrix A together with negative A, you're going to get back the zero matrix. So that means that every element of this set has an additive inverse. Since addition of m by n matrices is a commutative operation, that means that this is an example of an abelian group. Okay, next let's talk about multiplication of n by n matrices with real coefficients. We've already established that that's an associative operation, and for a multiplicative identity here, we can take the n by n identity matrix, with all ones down the diagonal and zeros everywhere else. It's a basic fact about matrices that when you multiply this matrix on the left or on the right by any n by n matrix, you don't change the other matrix. Okay, now how about existence of inverses? If I take an arbitrary n by n matrix, call it A, can I always find another matrix, B, with the property that A times B equals B times A equals the identity matrix? Well, you should know from linear algebra that an n by n matrix with real coefficients is invertible if and only if the determinant is non-zero. It's easy to give examples of n by n matrices with determinant equal to 0. For example, the zero matrix. So that means that there will always be some matrices in this set which don't have multiplicative inverses. That means that the n by n matrices together with multiplication of matrices is not a group. Okay, now for an example that I really like. What about if we consider the collection of 2 by 2 matrices with real coefficients and determinant not equal to 0 together with the binary operation of multiplication? The 2 by 2 identity matrix has determinant equal to 1. So it's an element of GL2R. And just like in the previous example, it serves as an identity with respect to matrix multiplication. So now the question is whether or not every 2 by 2 real matrix with non-zero determinant has a multiplicative inverse. You should remember from linear algebra that if you have any 2 by 2 matrix A with real coefficients and determinant not equal to 0, then there is another matrix B, also with real coefficients and determinant not equal to 0, with the property that A times B equals B times A equals the identity matrix. That matrix B is what you call in linear algebra the matrix inverse of A. And in case you've forgotten about that, you'll probably remember this formula. If the coefficients of the matrix A are A, B, C, D, and the determinant, which is AD minus BC, is not equal to 0, then the inverse matrix is the reciprocal of the determinant times the matrix D negative B negative CA. Well, anyway, the point is that every element of this set has a multiplicative inverse, so this is an example of a group. Now, earlier in the video, we showed that there are examples of matrices in this set which do not commute with each other when you try to multiply them. So this is our first example of a non-abelian group. Okay, now we have one example remaining, which is the set difference operation on the power set of a set S. We already said that this is an associative operation, so to check whether or not this is a group, first let's decide whether or not there's an identity element. Is there an element of the power set of S with the property that, when you set difference it with any other set, from the left or from the right, you don't change the other set? Well, to answer that, you need to think about the definition of set difference. Maybe looking at a Venn diagram might help you to guess what the identity element should be, but I'm just going to tell you, it turns out that we can take the identity element to be the empty set, which of course is a subset of any set S, so it's an element of the power set of S. Well, if E is the empty set, then for any set A in the power set of S, when you compute the symmetric difference of E with A, which is the same as the symmetric difference of A with E by commutativity, you get A set minus the empty set, union the empty set minus A. Well, the first piece here is A, and the second piece is just the empty set. So the union of these two sets is A. That means that the empty set plays the role of an identity for this binary operation on this set. Okay, next we need to think about inverses. Suppose that A is an element of the power set of S. Is it always true that I can find another set B in the power set of S with the property that the symmetric difference of A and B is equal to the empty set? Once again, you need to think about the definition of symmetric difference before you answer this, and it might be helpful to also look at the Venn diagram that illustrates what the set difference does. But after you do that, you're probably going to realize that if you let B equal A, then the symmetric difference of A and B, which again is the same as the symmetric difference of B and A, is just A minus A union A minus A, which is the empty set union the empty set. Therefore, it's just the empty set. Since the empty set was our identity element, this shows that every element in the power set of S has an inverse, and it allows us to conclude that the power set of S together with the binary operation of symmetric difference is an abelian group. Well, that's the end of that video. I hope you enjoyed it. We're going to see lots more examples of groups in coming videos, but in the next video we're going to talk about basic properties that all groups satisfy.